Hi, this is Mr. T with a tutorial on calculus, and we're in a series dealing with sketching curves of functions. And in this lesson we're going to be talking about how we find the concavity of a function. So what do we mean by concavity? Concavity is a shape, a way a function curves, and a function can either be concave up, meaning it holds water, so the curve of the function might look like that, bend that way. That's concave up. And concave down is the opposite way. It spills water, so it's bending that way. And there are things called inflection points, and those are points where the function changes direction. So if we had a graph that went, say, like that, say a cubic function or something, this point here where we switch from being concave up to concave down, the coordinates of that point is called an inflection point. And what we're going to talk about is how we use calculus to find out that information for any function. In calculus, the definition of concavity is a function is concave up. Now this is going to be an interval of x values when the second derivative is greater than 0. And it's concave down if the second derivative is less than 0. Inflection points occur when the second derivative is equal to 0, but that is not enough to determine an inflection point. It has to equal 0, but also the function must change concavity on each side of x, of that point. And we have to be able to calculate a y value, meaning the point has to be defined, so the original function must be defined at that particular value of x. So let's go through an example. So here we have a function, and we want to find the intervals on which that function is concave up, down, and any inflection points. So in our definition we had to find the second derivative, so to find that we have to find our first derivative first. So let's rewrite this function as this, so we can use our chain rule to make the first derivative. So using our chain rule, we're going to take the exponent times here, we get -6, and we subtract 1 from the exponent, and then using the chain rule we have to multiply by the derivative of what's inside, which would be 2x. And we can use the commutative property of math to combine those two things, so we have here -12x times x squared plus 3 to the -2. Now since we're going to be finding the second derivative, I'm not going to adjust that negative exponent, but we do also have to recognize, since I have an x out here and this, we have to use a product rule. So the u, when we use the product rule, is going to be -12x, and the derivative of u prime, will be -12, and v is going to be x squared plus 3 to the -2 power, and we take the derivative of that using our generalized power rule, subtract 1 from the exponent, multiply by the insides, or the derivative of the insides, and we get here -4x times x squared plus 3 to the -3. Now those of you who have watched my tutorials before, to get the product rule here, we're going to cross multiply. So I've got f of x, or this is f double prime because we're taking the second derivative. If we cross this way, I've got -12 times -4 is 48. And I've got x times x is x squared, and now I have this quantity, x squared plus 3 to the -3. And now I'm going to multiply on that diagonal, and I get -12 times x squared plus 3 to the -2. Now we're going to be trying to look at this as less than 0, equal to 0, greater than 0, so we want it in factored form. So we're going to GCF factor this, so we're going to factor out a 12, There's no x over here, and then we've got our x squared plus 3, so we factor out the lowest exponent. And now we find out what remains after we factor out our leftovers. So if we divide here, 48x squared divided by 12 is 4x squared. And these terms cancel out. Now when we divide this by our GCF, negative 12 divided by negative 12 is negative 1. And here we subtract the exponents, so negative 2 minus a negative 3 is plus 1. We can combine our like terms. So I have here 3x squared minus 3. And I can factor a 3 out of this, so I'm going to get 3 times 12 is 36. And I'm also going to move this to the denominator, so if I put up here our second derivative, I'm going to get 36 times x squared minus 1 over x squared plus 3 to the third power. Now to solve the inequality for f prime double prime of x less than 0, greater than 0, and to find inflection points, we're going to use our number line method, and we want to find when this derivative, this second derivative, equals 0 or where it's undefined. When we have a rational function, to find it equal to 0, we're going to solve our numerator for equal to 0. And to find where it's undefined, we're going to set the denominator equal to 0. So on the top, I've got x squared minus 1 equals 0. So if we solve that, we're going to get x is plus or minus 1. And if we try solving x squared plus 3 equal to 0, there's no solution. So we don't have any points where the second derivative is undefined, and we have these 2 points where it's equal to 0. Now we're going to organize that on a number line. And we're going to pick test points in each of those intervals. And we're going to evaluate f double prime in those test points. So if I pick a big negative number and put it in, the 36 will be positive. If I put a big number here, a big negative number squared is a big positive number, minus 1 is positive. Now our denominator, no matter what number we put in for x, is going to be positive, because x squared is positive, we add a number, so this is always going to be positive. So we have positive, 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 that's concave up. In this interval I'm going to pick 0, so I've got positive. Here I get negative 1, which is negative over positive, so I'm concave down. And over here I've got positive, positive over positive, or concave up. So we've got 2 intervals of concave up, 1 interval concave down, and at these 2 points, at negative 1 and 1, we're going to have inflection points because we change concavity. So let's kind of summarize this. We've got concave up on the interval, so going from negative infinity to negative 1, and then also 1 to infinity. We're concave down on the interval between negative 1 and 1. And we've got 2 inflection points. One is at negative 1, and then we need to figure out the y value, and the other one is at positive 1, and we need to figure out the y value. Now to figure out the y value here, we're plugging it back into the original function. So if I plug negative 1 in back over here, I get 6 over 4, or 3/2. And if I plug positive 1, I also get 6 over 4, which is 3/2. And that's our information that we were asked to find, and so we are done. So good luck on working your own problems, and see you around.